Hey guys, this is AP problem number 5, and starting off here with number 3, I guess it is, and letter A. Letter A is broken up into two questions. Calculate the number of moles of Cl aqueous present in before any reaction occurs. So for here we go to the information that's given up here, which is that we have in a 25 milliliter sample of 0.25 molarity NaCl. So that's pretty much all we need to run this first. So we got to know that molarity is moles over liters, and that isn't the right symbol for moles there, but yeah. So we put the molarity in here, which is the 0.250 molarity is equal to m over liters, which is this case, since it was in milliliters, you gotta use dimensional analysis to change that, and it would be to 0.0250 liters. And so here you just multiply these two together, and that'll get you 6.25 times 10 to the negative third moles of Cl minus, which is I1, or 1I, I guess, yeah. Now we got to calculate the volume in liters of Cl2 gas present in the sealed container. So for this one, this is a little more complicated. First, we have to figure out how many moles of Cl2 are present in the container, because it doesn't tell us. So to do that, we just do some simple stoichiometry, and we start with the number of moles given of Cl minus, I believe, which is what we did for I, and we multiply it by the molar ratio, which is up in the question up there, and it's 4 Cl minus to 2 Cl2. So pretty much you're just dividing the moles of Cl minus by 2, which is what this fraction goes down to, and you get 3.13 times 10 to the negative 3 moles of Cl2. So now we use the formula of volume is equal to number of moles times the constant times the temperature over pressure. So when we plug in all the information we have the number of moles of Cl2 gas, which is 3.13 times 10 to the negative third mole, times the constant, which is 0.0821 because we're using Kelvin. And actually in the problem they give us Celsius, but I like to work with Kelvin, so we transfer it over. So we add 273 to 22, which gets us 295 Kelvin. And then we put that over the pressure, which is also given in the question, which is 0.950 atms. And we plug this into the calculator, and you get 0.0797 liters of Cl2, which is the volume. And now we move on to question B, which is, if it'll focus in here, I'm sorry about that. We have to find the order of the reaction for the following. So we start off with I, which is Cl minus. And we go up here and we see that Cl changes in the trial of 1 to 2, and MnO4 and H plus don't change in those ones too. So that's one we're going to use. So we go here and we say that we use the reaction of 2 over the reaction 1 because we want the greater number on top. And we see that here we want the bigger one on top, so that's going to be the trial 2 over 1. So we put, it's not focusing, the 0.0321 over the 0.0104 inside the brackets with n, or parentheses I should say, which is equal to the rate of disappearance, which is also given in the table, and it is 2.03 times 10 to the negative 7 over 2.125 times 10 to the negative 8. And we put this into the calculator, and we see that this is 3 to the nth, and this is 9. And we just square root it, and we get n is equal to 2. And for II, which is you want to find it for MnO4, we see that in the experiment trial 2 and 3, Cl minus and H plus don't change, but MnO4 does. So we take the two numbers from there, which is the 0.004 and 0.002, and then the rate of disappearance. We put them in, and we see that we have trial 2 over trial 3. So it's going to be 0.00400 over 0.00200, which is equal to 2 to the mth. I forgot to put in the parentheses here. I shall fix that real quick. And that'll be to the m power, and which is equal to 2.03 times 10 to the negative 7 over 1.02 times 10 to the negative 7, which is, both sides end up being 2, so m is 1. And that does it for question B. Now moving on to letter C, which is also two-part. And so we know now that H plus is a third order reaction, so now we have to find the rate law for this. So the rate law is just it together, and as we see here, it is rate is equal to the constant to times bracket Cl minus to the second power, which we found right there, and times MnO4 minus to the first power, which we found there, and H plus to the third, which was given in there. So now we found that, we found the rate law. Now it asks to find the constant. So to do this, I selected the trial number 1 and used the rate of disappearance there and plugged it in for the rate. And then I went and got these numbers from there, from trial 1, and put them into there, and squared the first one, did nothing to the second one because it's MnO4 to the first power, and then cubed the H plus because it is supposed to do that. And then you get 1.17 times 10 to the negative 5th power, so you divide that by both sides to cancel it out, and you get 1.93 times 10 to the negative 3. I believe that's molarity per second over, it would be m over s, I believe, is also what it is, written a different way. And I'm not sure if that unit is right, though. Let me move on to D, and it says that it is likely for this reaction to occur in a single elementary step, and you have to justify your answer. Oh, is it likely that the reaction occurs in this step? Justify your answer. And I said no, it doesn't, because if we look at the rate law, the orders there don't match up to the coefficients that's given in the problem, and that's why it doesn't happen in one elementary step. Thank you. That was AP problem number 5. Thanks for watching.